In the previous segments, we looked at the definition of Markov chains, and we looked at the notion of what makes some Markov chains more interesting than others, and we classified the states of a Markov chain and generally built an understanding of Markov chains. In today's segment, we're going to delve a little deeper. We're going to also look at an application, and inspired by that application, we're going to study the notion of stationary distribution of Markov chains. Okay, so let's start by looking at this application. One of the key things about big data is that the data changes over time. The data is never static, and it keeps changing over time, often in a fairly slow manner. Okay. And let's look at a concrete example. Let's look at the list of celebrities. And this list is ordered by popularity. So number 1 is the most popular celebrity, number 2 is the second most popular celebrity, and so on and so forth. And this list is not static. I mean, this list has, I mean, at any point in time, such a list exists, but obviously the list way back in, say, 1950 is going to be very different from the list that we have in 2016. So the list keeps changing over time. So for our purposes, we're going to look at this list in this formal sense. We have a list of celebrities ordered by their popularities, and some phenomenon, natural phenomenon takes place, maybe a hit movie or a hit song or a scandal or whatever, changes the ordering of the popularity of the celebrities. And how do we model that? We allow basically a random consecutive pair is chosen uniformly at random, and the more popular of the two will be made the less popular one, and the less popular will be made the more popular. So basically swapping their popularities. And this phenomenon can, so this process itself is a random process, and over time the popularity or list keeps changing. Okay. And given such a changing list, we're interested in maintaining the most popular celebrity, and we want to do this without expending too much effort into it. And so here's a very simple algorithm for it. At any point in time, just maintain the most popular celebrity that you have currently seen so far, and you randomly probe a new celebrity and check if this new celebrity that you've probed randomly is more popular than the celebrity C or not. And if the probed celebrity is more popular, then you update C. That's it. It's a very simple natural algorithm. It's a perfect algorithm that can just run in the background, and eventually we hope to be able to report a celebrity that is fairly popular. I mean, the celebrity, this due to the dynamic nature, we may not always report the most popular celebrity, because the moment the current celebrity C that you have, even if he or she is the most popular one, due to dynamism can move down the list, and by the time you correct yourself, it's going to take some time. So we cannot guarantee that we're always going to be reporting the most popular celebrity, but we want to be able to report a fairly highly popular celebrity. Okay, so we want to characterize how good this algorithm in that sense. But in order to do that, we need to build an understanding of the theory of stationary distributions, and that's what we're going to do now. Okay, recall that we use the notation P to denote the one-step transition matrix. Okay. And what is a stationary distribution? It's basically a probability distribution given by pi 0, pi 1, and so on up to pi n over the set of states in the Markov chain that obeys a condition. What is that condition? Pi equals pi times p. notice. So you can think of this uh, distribution as the state in which the Markov chain will be infinitely far out into the future in once it's reached some steady state. So if the Markov chain is going to be in its states, in one of the states 0 to n, in accordance to this probability distribution, then it will continue to be in one of those states according to this probability distribution. So it's some sort of a steady state behavior of the Markov chain. And that's usually what we are interested in the context of Markov chains. We are interested in the steady state behavior of the Markov chains. Okay. Here's a point in time we should take a few moments to design a simple Markov chain with multiple stationary distributions. And even if it means that you need to pause for a few minutes, please do that. But think about it carefully and design a Markov chain with multiple stationary distributions. Okay, but eventually our interest is going to be finite, irreducible, and ergodic Markov chains. But don't worry about that. You just need to design a Markov chain that has multiple stationary distributions. Let us now look at the fundamental theorem of Markov chains. And since we are interested in finite, irreducible, and ergodic Markov chains, that's what this theorem is going to talk about. And such Markov chains have a unique stationary distribution. Okay, so and if it has to be unique, that means essentially the history is forgotten. Whatever be the way the Markov chain starts, eventually it's going to reach a steady state where the distribution is going to be the same. It cannot lead to multiple different distributions. It can only lead to one unique stationary distribution. So that's very important. Okay, and secondly, the theorem states that well, let's first remind ourselves what P subscript j comma I superscript t is. It's the probability that a Markov chain that is currently in state j will be in state I after t steps. So it's currently at state j, and after these t steps, the probability that the Markov chain will be in state I is this P j comma I superscript t. Okay, and we're interested in that probability with t tending to infinity. Okay, and this theorem states that that probability exists, and moreover, it's independent of j. So this little j really doesn't matter. Regardless of where you start, as t tends to infinity, this probability is going to converge to the same value. And finally, let's remind ourselves what HII is. HII is the expected number of steps for a Markov chain at state I to return to state I. So you're at state I. How long does it take to take a walk, but then return back to I? And that's, if you look at 1 over HII, it gives you a sense of how frequently you will be coming back to state I. And quite naturally, that frequency is exactly equal to this limiting probability as t tends to infinity, that p j comma I superscript t. And that's exactly our pi I, the probability with which at steady state the Markov chain will be at state I. Okay. So this is our fundamental theorem of Markov chains. Take a few minutes to pause and make sure you understand the statements. The proof was also present in the textbook, but we're going to skip it for the purpose of our lecture. And just to reinforce our intuition, let's make a few nice observations. Notice first that the Markov chain for a finite, irreducible, and ergodic Markov chain the stationary distribution is going to be such that no part of the maze is going to be left unexplored. No, every state is going to be explored. So all the pi i's are going to be strictly positive. Okay, and there's going to be a unique steady state behavior. Initial conditions are forgotten. So it doesn't matter how you start, eventually the Markov chain is going to end up in a steady state behavior. And there's a nice clean intuitive relationship between pi I and h I. That's pi I equals 1 over h I. Okay. Now that we know what a steady state or what a stationary distribution is, and we're now interested in computing the stationary distribution, and so we have several ways to do that. The most obvious way is to simply solve a system of linear equations directly falling out of the definition of stationary distribution. So a particular vector pi would be the stationary distribution if and only if it obeys this equality: pi equals pi times p. And you have also one more equation. Since this pi is a probability distribution, if you add up the components, it has to add up to 1. So you get that as well. Okay, so that's just solving this system of linear equations is going to give you a way to solve for pi. But this is not very feasible if the number of states in the Markov chain is very large. So there's probably more intuitive ways to do that, and one of them is the cut sets method. And so let's warm up first. Consider a very simple but nevertheless very useful Markov chain. So it simply has just two states, 0 and 1. And with probability p you go from 0 to 1, and with probability q you go from 1 to 0. Okay. And these Markov chains, this simple Markov chain can be used to model a variety of things where there's two states, say a good behavior and a bad behavior. What's the probability? So you may be interested in understanding what the probability is that you are going to be in the good state versus the bad state. And this, as you can see, naturally leads us to the notion of stationary distribution. So we're interested in understanding the stationary distribution or the steady state behavior of this Markov chain. And so there's a very clean intuition behind this Markov chain. So let's just consider the cut dividing state 0 and state 1. The frequency with which the stationary distribution moves from state 0 to state 1 must be equal to the frequency with which it moves from 1 to 0. And this is some sort of a law of conservation of Markov chains, if you will. I'm making that up, but gives you some notion that you really cannot lose the Markov chain when it goes from one side to the other. So if it goes from one side to the other, it has to come back from the other side back to the former side, and so on and so forth, right? And we can use that to actually compute the stationary distribution. So here's how to do that. This notion of the frequency with which the Markov chain goes from left to right and right to left, these can be captured by pi 0 times p. Pi 0 is the probability with which the Markov chain is going to be at state 0. And given that it's in state 0, it will actually move to the other side of the cut with probability p. And vice versa, pi 1 times q. And these two are equal, according to our intuition. Okay, so great. So we have one equation. And the other equation, of course, we can always resort to summing up the probabilities in the distribution, and it has to add up to a 1. And if we solve them, we get pi 0 is q over p plus q, and pi 1 is p over p plus q. So as you can see, we now have a handle on the stationary distribution of this simple but nevertheless very useful Markov chain. And this notion can be generalized to Markov chains with more complex structure. We'll see one such Markov chain in the subsequent segment. The third technique to compute the stationary distribution applies only to time reversible Markov chains. A Markov chain is said to be time reversible if for every pair of states I and j, this equation holds. Pi I times the probability of transitioning from I to j equals pi j times the probability of transitioning from j to I. Okay. And why this is called time reversible? Well, we're going to have an exercise problem dedicated to gaining an understanding of why this is called time reversible. So for now, let's just keep this definition in mind. And let's look at a theorem. Now, the theorem does not depend, as far as the statement goes, does not depend on time reversibility. But as you can see, this theorem will only be applicable when the Markov chain happens to be time reversible. Okay, if you can guess a vector, pi 0, pi 1 up to pi n, so and you want you hope that this guess is going to be the standard deviation. Sorry, this guess is going to be the stationary distribution. And if you can furthermore show that for all pairs I and j, pi I times pij equals pi j times pji, then the guess is in fact a stationary distribution. And of course, you also want the summation overall pi i's to equal 1. Okay, and if this is sort of a guess and check technique for computing the stationary distribution of a time reversible Markov chain. Okay, so we've now built sufficient ideas about stationary distribution and Markov chains and so on and so forth. What we're going to do in the next segment is we're going to go back to the problem that we talked about in the starting at the start of this segment, and we're going to revisit that problem, and we're going to gain an understanding of how good a celebrity we will be, that simple algorithm will be outputting. And we will, in that process, exercise several notions of Markov chains and stationary distributions.